Now let's go ahead and talk about another type of visualization. So we've looked at histograms. Now we're going to talk about box plots. And in order to dive into box plots, we need to know a couple different statistics that we haven't talked about yet. So just like histograms, box plots are used as a way to visually represent quantitative data. And with box plots, we can actually divide our data into equal sized segments called quartiles. So these are the statistics that we haven't talked about yet, but they come up a lot with box plots. So the quartiles that we're going to look at are Q1, Q2, and Q3. In other words, we're going to look at the first quartile, the second quartile, and the third quartile. So I like to think of these in terms of percentiles. So Q1 is actually the 25th percentile. In other words, if you're at Q1, if you're at the 25th percentile, there is 25% of the data below that value. Q2 is the 50th percentile, and then Q3 is the 75th percentile. So we have on this sheet the 12 random responses from the probability words data set. And we're specifically looking at the words we, or the numbers for we believe. So we've divided this data into quartiles. We're looking at the first 25% of the data, the next 25%, next 25%, and final 25%. And a box plot is going to show those Q1, Q2, and Q3. So the second quartile is also known as the median. And we've seen the median looking at our descriptive statistics, and we know that the median is essentially the middle number. It's the point in the data set where you have half of the data below that number and half of the data above that number. So Wade, do you want to help me out with calculating how to calculate Q1, Q2, and Q3?
Yeah, let's do it.
Sounds good. So we want to go ahead and look at how to calculate these mathematically. So when we calculate Q2, we said if it's between two numbers, we find the midpoint between two numbers. So I think we looked at data sets that have, or variables that have an even number of data points. We said there's going to be two middle numbers, so we'll just go ahead and take the average of those to find the median, or Q2. And this works because Q2 is the 50th percentile. There's 50% of the data below and 50% of the data above Q2. However, when calculating Q1 and Q3, unfortunately, we do not just take the midpoint. We have to do something else.
And this is really interesting because there's a lot of different ways that we can think about taking the center value between two numbers when it's not the center of the data set.
Exactly. So instead of just taking the midpoint for Q1 and Q3, we want to make the best possible estimation of that true value, of the true value of the first quartile and the third quartile. So if we look at this data, this is the same data as above, the data for we believe, the 12 random observations. And if we actually divide this into 4 equal quartiles, we can see that for Q2, for the median, this is going to be right in between these two numbers. But for Q1, the first quartile, this isn't actually just going to be 65, the number in between 60 and 70. So instead, we have to find the true location of where that value lies.
And if we think about the number between Q1 and Q2, that Q1 number is 25% of our data is to the left.
Exactly.
And 75% of our data is to the right. So we don't want it exactly in the middle because we have this idea that we have 25% of our data, less of our data is on the left-hand side of it, and more of our data is on the right-hand side of it. So we're going to have a formula to see how far are we in between two numbers.
Yes.
So how would you calculate this, Carly?
So basically, there's kind of a formula that we can use to find the true location, and then we can find that exact value in this data set. So we are going to use this formula, which basically says we're going to take all of the data points, the number of data points, and subtract 1. So we're going to take the number of data points minus 1, and then we're going to multiply that by the percentile of interest. Percentile we want to find. So in this case, we're looking at Q1, so that is the 25th percentile. how many data points did we have here?
So we've got 12 data points.
Okay, so I'm going to take 12 minus 1 times, and then the percentile of interest is going to be 25. So should I put that as 25, or do we want to use a different number?
We can use 25%, but as a fraction, it's going to make a lot more sense. So we don't have that percent sign laying around. So that's just going to be 0.25.
0.25. And what do we get for the true location of this value?
The true location index is 2.75.
2.75. All right, so that is the true location of where this number actually is.
So what this means is if we label the numbers as indices, starting from 0, we can go 0, 1, 2, 3. And I usually label that right underneath those numbers like you did.
Let's go ahead and do that.
And then 2.75 means the true location of the 25th quartile, or the 25th percent, when it's between two numbers, is basically index 2.75 on the list. So it's slightly closer to the third index number than the second index number.
Yes, so now let's use that to go ahead and find Q1. Let's actually find the value. So basically to do this, there's another kind of formula that we can use. We can basically take the lower number in between those two indices, so in between 2 and 3. So I'm just going to call that the low. So I'm going to take the low, and then I'm going to add the high minus the low. And then I'm going to multiply that by I'll call it the fraction percent, which basically what I mean there is this 0.75, the part after the 2 in the 2.75. And so when I say high and low, just to be clear, I know that Q1 is in between 60 and 70. So that's the numbers indexed at 2 and 3. So I'm going to call 60 the low, and I'm going to call 70 the high. So if I plug those numbers into this formula, I get 60 plus 70 minus 60, or 10, times this 75. So I'm going to do times 0.75.
And if we multiply this all out, 60 plus 7.5 is 67.5.
And that actually gives us the true value of the 25th percentile, or of Q1. So we can see we didn't just get the number in between the midpoint of 60 and 70. We didn't get 65. We actually got 67.5. And this is a better estimate than the midpoint. So that's what we're going to go ahead and use. And wait, is this what Python uses?
That's exactly what Python uses. And that's the reason we're choosing this technique above all of the other techniques to calculate the midpoint between 2 points. And we can do this not just for the 25th percentile, but any percentile. And if we use this formula for a 50th percentile, it's going to take the equal contribution from the high and the low number, because you're multiplying by 0.5. So you're going to get the same answer, even if you use this formula for the 50th percentile.
That sounds great. And as data scientists, we definitely want to have our statistics and computation in line with each other. So it makes sense that we're going to use exactly what Python uses. So a couple more things to talk about with box plots. One measure of spread that's very visible from a box plot is something called the interquartile range, or you'll see me abbreviate this as IQR. And this is basically just the middle 50% of the data. So like the standard deviation in the range, it's another measure of spread, and we can calculate it by taking the third quartile and subtracting the first quartile. So in other words, I have the 75th percentile minus the 25th percentile, and that gives me the middle 50% of the data. And on a box plot, this is actually the width of the box. So we're going to see that in our example in a bit. The very last thing that I want to cover on the box plot is outliers. So box plots are really good for displaying data that has extreme outliers, because outliers on box plots are actually plotted as dots, as individual dots, so you can see them really well. And I like to say that outliers are points that lie outside of most of the data. They're points that differ significantly from most of the other points in the data set. So in statistics or in data science, oftentimes outliers can be things like typos. We don't want typos, but sometimes maybe if you're typing into an Excel sheet, you might add an extra 0. You mean to type 100, you type 1,000. That could show up as an outlier. Sometimes they can be lies on surveys. Sometimes people put outrageous answers on surveys just because, and then you can get an outlier from that. Or even, I guess most importantly, outliers can be real data. Sometimes you just happen to have outliers. And so we want to know for our box plots what values are outliers and what values aren't. So we can calculate out outliers mathematically using the following rules. So low outliers are any numbers that are going to be less than Q1 minus 1.5 times the IQR. So any numbers in your data set less than that quantity are going to be low outliers. And then high outliers are any numbers greater than Q3 plus 1.5 times the IQR. So kind of very similar formulas, just slightly different. And we can find our high outliers by looking at our data set and saying, are there any numbers bigger than whatever we get for this quantity? The next question is, how do these outliers affect our data set? Why do we care about outliers? And we know that outliers are going to cause our mean specifically to be much greater or smaller than it would be. We have talked about how mean and median, the measures of spread, can be affected by extreme outliers. Mean specifically are affected by extreme outliers. Medians not so much. Outliers will also increase our spread, or our, I'm going to say our standard deviation and range. Standard deviation, range, and variance. So they definitely increase our spread. And then outliers, we said, may affect the median, but if all the other values in the data set are close together, the outliers generally don't have as much of an effect on the median as they do on the mean. And we actually have an example of a box plot that was created from Python here below. And we have the Python code, which Wade is going to talk about in a lot more detail in this series later. But I want to just kind of look and see exactly what this is telling us. So looking at this box plot, I can see we have two low outliers. There's one at 0 and there's one just above 40. So remember, the outliers are the single dots. The box tells us our Q1, the bottom part of the box, Q2, the middle line, and then Q3, the top part of the box. So we know exactly what those values are, and we can see them represented here on this box plot. And then the whiskers actually tell us, if there's no outliers, what is the max or the min. So we don't have any high outliers, so this top whisker is just going to be the maximum value. And then the bottom whisker, we actually do have outliers. So this is going to be the lowest number on our list that is not an outlier. So this is the lowest number that's not an outlier. And this box plot tells me that for we believe, most people said that is between, it looks like about 70 to just above 80%. And that we do have some low outliers. So somebody said we believe was 0%.
Yeah, I think it's just 0.1 in the actual data set.
Yeah. Oh, so not exactly 0.
Not quite 0, but basically 0.
So this could have been someone who didn't understand the question, or maybe they were a liar and just put a weird answer just to be weird. So that is it for box plots, and we're going to dive even more into the Python code in the next couple of videos.